operations with functions as the intro to our exponential and log unit. This morning I made a decision to go straight into the exponential log unit and kind of bypass the modeling unit. That way when we get to the modeling unit, we can do exponential and log functions. If we taught it in the other order, we couldn't. So here we go. I love today because it's great for right before a break. It's kind of one of those no-brainer kind of lessons. As long as you're awake and breathing, you should be fine. Alright? So the first thing says to add F and G. So what do you think we do? We would add them. Yes. Alright, so we would take F. Whoops, that's minus. And we would add G to it. So F plus G results in this polynomial, 3x squared minus x minus 4. Okay, F minus G is exactly what you think it should be. It's write down F and subtract G from it. Okay, now if you tend to drop negatives and stuff like that, you might want to go ahead and distribute this negative by changing your signs. You don't have to. If you can actually in your head go, oh, I subtract this and I subtract that, then you're fine. So 2x squared taken away an x squared is just an x squared, and then minus x, and then plus 6. Alright, now what if you saw function f right beside function g? Or function f with a little bitty dot beside function g? What do you think we're going to do with these two functions? Multiply them. So we would write down f. We would write down g. And we will multiply them. So I would probably distribute g through f. You could go either way. Okay, go ahead and do that distribution, and let's see what you get when you combine my terms. Okay, so we have 2x to the 4th minus x cubed minus 9x squared plus 5x minus 5. Okay, now, when we think about function f, if we were to think about its domain, are there any values that x could not have?
No.
No. The domain of this function would be negative infinity to positive infinity. Well, that was terrible. Let me try again. All right, what about function g? It's the same. The domain is also negative infinity to positive infinity. So, if I put them together, would there be any restriction on the domain? Not necessarily. All right, so, no, not in any of those cases. But let's look at what happens when we do the next thing, which is division. So we have two new functions. We have h and n. I don't know why I chose h and n, because if you don't put the little stick on it long enough, they look like the same thing.
Can we do H and N?
Sure. Okay, when we look at h and n, h has no restriction, n has no restriction, but when we put them together, we have a problem. Okay, with division, there's not much I can do. All you can do is write this over this. Now, if the numerator factored and I was able to cancel anything, then it would be nice. But this numerator doesn't factor, does it? There's nothing that I can multiply to get 7 that I can add to get -5. The numerator does not factor over the set of integers, and the denominator is already linear, so it doesn't factor either. So I can't do any canceling here. I can't reduce anything. But with division, when I put them together, I went from something that had no restriction on the domain, no restriction on the domain, but when I do division of those functions, now I'm going to have a restriction on the domain. Because this denominator can never equal what? 0. 2x plus 3 could never equal 0. Because if it does, then this becomes undefined. So, with division, we have a restriction. And this is how we would solve it. And you may be able to just look at it and tell that it's -3/2, and that's fine. So there's a two-part answer to a division problem. Because of the restriction on the domain, part 1 is state the division. Part 2 is state the restriction on the domain. X cannot equal -3/2. So division has that two-stepper because it will have that restriction. All right, so here's another example. Now this one's kind of cool because when we do f over g, we get 2x squared plus 2x over x plus 1. Okay, so we already know what the restriction is. What can x not equal? -1. -1. But this actually simplifies, so I wouldn't leave it like this. Do you see that the numerator has a common factor? What's the greatest common factor of the numerator? 2x. And when we factor that out, we are left with what? X plus 1. But the denominator was x plus 1.
So those cancel out.
So this binomial cancels with that binomial, and we are left with 2x. But we still have the original restriction. Now, to make this kind of make more sense, let's pull out our graphing calculators, and I want you to enter this under y1. And we're going to do some investigating about what's going on right there where x is -1. Alright,
Apparently there
go
were
to the table.
quite a few people that passed out today giving blood.
There were? Yeah. Okay.
What they did, they set up curtains so that people would not see and they'd be more calm.
I've never passed out giving blood, but I had to quit giving blood when we used to have hour-long classes, and that was enough time for a teacher to go give blood and then come back and teach. You shorten them by 10 minutes, and I don't have time to go give blood and then recover and come back and teach. After they shortened the classes, one time I ran back to my class to try to teach. And as soon as they pulled out the needle, I'm like, I'm good, thanks. Where's the nutty bars? Gotta go. And that didn't work out. So I don't try it now. Yeah.
With your parents' permission.
It was rough.
I hate age restrictions. They're stupid. They're not acceptable.
Or they're responsible.
No, they're really not. See, because everybody's different. Would you agree? So everybody has different maturities. So I would agree for some people that 16 is too low of a number for them to be able to drink.
Okay.
And for others, 16 is too high.
All right. When you look at the table, did you notice there's an error right there at -1? Okay.
Wait, mine doesn't look. Oh.
Yeah, mine don't look like that.
Do we have to put parentheses? Is that why?
Here's the equation.
Yeah, I didn't.
Okay.
So it had to be in
Now,
parentheses.
you don't have this little circle right here.
I guess we had to put in parentheses.
Okay? I put that little circle right there. Yours should look like this. Yeah, you had to put parentheses because everything was in the numerator and then everything else was in the denominator. So yes, parentheses were critical to get the correct graph. So add those parentheses if you need to.
Why is it different than if it's just like y equals 2x?
Okay, it looks like y equals 2x. This is a straight line that has a slope up to over 1. And it passes through the origin. So if I looked at that line, that is y equals 2x. But it is not defined where x is -1. Because that value in the table where x is -1, if we plug -1 into the original function, we would have 0 in the denominator. So what it means is, and this is fun, you'll do this in pre-cal, when you graph these, there's actually a hole in the graph right there. It's continuous on this side, it's continuous on this side, but right here, there is no point. Where x is -1, there is no point. There is a hole in the graph. Okay?
Why don't we have the hole?
I forced the hole there. See, my graph looks just like this. So you're not going to see it on the graphing calculator, but you do see it on the table.
Oh.
The table tells you there's a hole there. But you can't, the graph doesn't stop. I don't know if you zoomed in, if maybe, probably not. I don't think so. I don't think they programmed them in such a way to show you the holes.
Nah, I don't think we're that advanced yet.
So that's interesting. We have to, must keep that restriction. Because really, this does simplify to just that simple y equals 2x. But there is no value where x is -1. The function is undefined there. And it causes a hole in the graph. So when you simplify it, you must still state the restriction on the domain. This works for everything but -1. Make sense? Okay, cool. All right, so addition, subtraction, multiplication, we didn't have to worry about any of that. There were no changes. Division, we have to worry about it. Okay? All right, the second part of today's lesson is composition. Now, I think you guys have done some composition.
I think you showed us on the board.
Yeah, you showed us
Like one time.
Okay.
and there were like 4 F's.
Yeah.
And it was like
Oh yeah.
a
And
lot.
you
Yeah,
showed
that
us that
scared
it
us
wasn't
all.
as bad as it actually was.
Gotcha.
I don't remember what happened.
All right, maybe you haven't done composition before, and this is still easy. Okay, so what we're going to look at is composition. And first we're just going to do some evaluating functions. So here I have function f and function g. Now, let me explain what this means. What this is telling us to do is to evaluate function f when x is 2. So we plug in 2 for x. 2 squared is 4. 4 times 2 is 8. And 8 minus 1 is 7. So f of 2 has a value of 7. And that's how we would say it. F of 2 equals 7, which means when I plugged 2 into function f, I get out 7. This is just telling everybody, hey everybody, I just plugged in 2. Okay, so if you had never seen it before, you might try to divide by 2 right now. This is not f times 2. This is telling you, you plug 2 into function f. Okay, now this says, hey, plug 2 into f, and then plug that into g. Okay, so we already know what f of 2 is. We just found it. It is 7. So we know f of 2 is 7, so now we find g of 7. So when we plug 7 into g, we get 7 plus 2, which is 9. So g of f of 2 is 9. Now, this type of composition is probably what you'll see mainly in pre-calculus and in calculus, but the open circle, a small open circle, means the same thing. Now, a small open circle you'll see in the textbook, but I think on standardized tests, most of those are using the nested parentheses. I like the nested parentheses because it appears as if you're actually plugging this into here. It looks like it gets plugged in. This doesn't look like that to me, but it means the same thing. So this says find f of 2, and then take that answer and plug it into g.
I don't like that as much.
I don't like that notation as much either, but it means the same thing. So this just means that. Okay, so this says plug 1 into g. Okay, if we did g of 1, what do you get out? 3. So now we plug 3 into f. Yes. 17. And then where does 17 go? Into G. 19. Okay. Now this says plug 5 into G. When I plug 5 into G, what do I get out? 7. And now it says plug 7 into G. And you get out 9. Yeah,
This is easy.
I agree. Today and tomorrow are not hard, which works out really well since you're kind of over it. I know.
I'm so.
Okay, now, do you see that these don't have values for x? So instead of just plugging a number in, we have to take this whole function and plug it in.
Yeah. Now it's
Okay?
making it fun.
This is the hardest thing we do all day, and this still isn't hard. Okay? So this says take all of G and plug it into F. So F was x squared. So instead of doing x squared, all of g gets plugged in right there. Okay, so did you get square first, double, front, square the last? Hey. Okay, so let's think about this one. This one is a line, domain, that. This one is a parabola, domain, that. So if I take this and plug it into this, did I change the domain at all? No. Okay, so this one, there's no restriction on the domain. The domain is still negative infinity to positive infinity. So when we compose these two functions, it turns into this quadratic, and there's no restriction on the domain. All right, so now let's go the other way. The other way says to plug f into g. So we have 2 times x minus 3. That's what g was, 2 times x minus 3. So what gets plugged in here? X squared. And so it's just 2x squared minus 3. It's a little disappointing. Nothing exciting right there. Okay, so once again, no restrictions on the domain, not causing an issue. Now, this function right here, we haven't really studied, but let's think about it. If I'm graphing it, only the things that will come out 0 or greater inside here will graph, right? Because otherwise it's the imaginaries, right? So, this one has a domain that goes from -1 to infinity. Graph this on your calculator.
That's so cool.
Graph that on your calculator.
It just kind of goes.
Yep. Okay. Do you see what the square root function looks like? Okay. Now, this one says I am taking that square root function and plugging it into f, which is a quadratic. Now, this one has a restricted domain. That restriction will carry through the composition. Because when I plug this in, what happens to the square and square root? They cancel. And I'm left with x plus 1, which sounds like a line, doesn't it? Okay? Type this into your graphing calculator and graph it. And look at what happens to that line.
That exact thing, parentheses.
Yeah, exactly like this. Parentheses, square root, squared, all that.
It's a line, but it still starts at -1.
Right. It is a line, but you don't get the whole line. Okay?
Part of a line.
You only get part of it. It starts right here at -1, and you get this side of the line.
Cool.
That's all you get. And the reason is because the domain restriction we started with. So this one has a domain from -1 to infinity. Now, just like the other composition, we could also use this open circle. So the composition of G with F can be written this way, or G of F of X. So these two things mean the same thing. Once again, I'm more fond of the nested parentheses, but there are textbooks that are more fond of this. So that open circle means composition. These things have the same meaning. All right, so if there is a restricted domain on what's input in, that domain carries. That restricted domain carries. And we saw it on our calculators. Make sense? Okay, I'm going to open up the homework on the screen for you to get started with, and I may see if I can go get us textbooks. I'm sorry, I didn't think to do that ahead of time.